Thank you, and a pleasure to be back here to give you, yes, the sequel to The Beginning of Everything. So as you can see from the subtitle, I'm really talking about ultimately the fate of the Earth, the fate of the Sun, the fate of the solar system, the fate of the galaxy, and by the end of the lecture, in 2 or 3 hours' time, we'll be talking about the ultimate fate of the universe. So if you'll forgive me paraphrasing Buzz, we're basically going to eternity and beyond. So very quickly, I'll give a very short prologue, and then in approximately chronological order, I'll be talking about the fate of the Earth, the fate of the stars and the galaxies within, the stars and other galaxies. And I'll be talking ultimately about the far, 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 far future and the ultimate fate of the universe. And in order not to leave you too depressed at the end of all of it, I'll summarize with a little epilogue on a slightly more upbeat note. So yes, I've already told you about the beginning of everything. I'm not going to recap all of that other than to remind you the universe, as far as we understand it, started about 13.8 billion years ago, and it took about 3 minutes to make all of the hydrogen in the universe. We know the universe is expanding, and that means if we wind the clock back, everything that we currently see was a lot closer together. So at the moment, the observable universe is about 100 billion light years in diameter. At the moment, that is a huge sphere, but everything, if you wind the clock back far enough, used to be a lot closer. If you wind the clock back far enough, everything in that 100 billion light years was only a few centimeters apart, the cosmic golf ball of 13.8 billion years ago. But we're looking forward rather than backwards in this particular talk. And in order to try and keep track of where we are in time, because we're going to be launching headlong into enormous distances into the future, enormous times into the future, we've got this timeline across the top here to try and keep track of where we are. So each small box represents 10 times further into the future than the previous box. So as time goes by, as my slides progress, a red rectangle is going to move across the screen there. So at 10 to the power 3, we're talking 1,000 years into the future. When we talk about 10 to the 6, 1 million years into the future, 10 to the 9, 1 billion years into the future, 10 to the 12, 1 trillion years into the future. So you get the idea, either in this talk or indeed on the handouts, that little red rectangle will just remind you where we are in terms of the timeline. And I'm indebted to the work of Laughlin and Adams and Laughlin here, who published a paper about 25 years ago on the chronological time that particular astrophysical events are likely to take place or are predicted to take place. And I've used that paper of the chronology of what's happening in the future to try and get my slides in the right order. So I'm not doing it thematically, I'm doing it literally by putting everything in the right time sequence, and I've used that paper as a guide. So I'm not going to start at the next 10 years or the next 100 years. Let's assume we get climate change under control. Let's assume we don't have a nuclear war. Then we know things are going to happen on a time scale of many thousands of years into the future. Some things are quite predictable. For instance, we know that the Earth's axis is precessing on a time scale of 26,000 years. It takes to do one circuit here, in the sense that the pole of the Earth is pointing to a particular point in the sky, which maps out a big circle on a time scale of 26,000 years. So we know on a time scale of about 10 to the 4, in 10,000 years, instead of the pole at the moment pointing towards Polaris, it's going to be pointing on the other side of this circle. The Earth's axis is going to be pointing in another 10,000 years or so, much closer to the star Vega. So there's a number of consequences to that. One is that when you ask a Boy Scout to find north, it's going to be a lot easier because they just have to find Vega rather than try and figure out where Polaris is. Obviously, Polaris is not as bright as a lot of people think. So it's going to be easier for Boy Scouts, but also it has consequences beyond that. So at the moment, for instance, we are nearer to the sun at perihelion during northern winter. But if the Earth's axis is pointing the other way, we're going to be nearer to the sun during northern summer. So that's going to exacerbate the seasons rather than mitigate the effect of being closer to the sun and the effect of tilting towards the sun. So we know there are going to be climatic changes in 10,000 years just because of the way the Earth's axis points. And generally speaking, whenever we see a variation in the Earth's climate, which is a function or which is a consequence of the tilt of the Earth or the direction that the Earth axis is pointing, or a change in the Earth's orbit around the Sun, those are collectively known as Milankovitch cycles. And we'll hear more about those in just a second. On a timescale of 10 to the 5 years into the future, voyagers are going to pass close to other solar systems and probably pass straight through other solar systems. So Voyagers were launched along with the Pioneers back in the 70s. Voyager 1 passing Jupiter, Saturn, Voyager 2 passing Jupiter, Saturn, and then Uranus and Neptune. And they are heading out of the solar system. Voyager 1 at the top of the graphic there is heading off in the direction of the star system Gliese 445. And down at the bottom here, Voyager 2 is heading off in the direction of the star system Ross 248. Pioneer 10 on the right-hand side is heading off in the direction of Aldebaran, and Pioneer 11 on the other side is heading off on the left-hand side of this diagram off towards the center of the galaxy. And on these timescales, we would expect all of those probes to start passing through other star systems. And during their lifetime, they will probably pass through hundreds, if not thousands, of other solar systems. Now, still on a timescale of 10 to the 5 years into the future, we know ice ages are coming. From the historical record, we know ice ages come and go on a timescale of about 100,000 years. And we also know that the Earth entered a warm period in between ice ages. It came out of an ice age relatively recently, and so we think the next ice age is due on a timescale of about 100,000 years into the future. And this is another manifestation of the way the Earth's orbit around the Sun changes. It's another manifestation of Milankovitch cycles. So we know the climate of the Earth is going to change, regardless of any man-made efforts to stop climate change. We know that there will be natural effects that change the Earth's climate. For quite a while, ever since the atomic age, in fact, we've known that the Earth's axis, the spin around the Earth's axis, is starting to slow. We know that the length of the day is now longer than it used to be because we've had atomic clocks which are accurate enough to be able to tell that the Earth is slowing down. If that continues for another 100,000 years, at the moment we're adding a leap second to our clocks, generally speaking, a few times every decade. We haven't done that for quite a while. We haven't added a leap second for the last 6 or 7 years or so. But for quite a while, we were adding leap seconds to keep the rotation of the Earth synchronized with our clocks. But if this slowdown of the Earth, because of the tidal drag of the moon, continues, then in 10 to the 5 years into the future, it'll not be a question of adding a leap second once every few years when it's necessary. If this continues, we'll need to add leap seconds every day. In other words, the length of the day will now be 24 hours plus 1 second, not 24 hours, give or take a fraction. So if this continues and the moon continues to drag the Earth and slow it down, then leap seconds will become more and more and more common into the future. We can't tell when stars are going to go supernova, but we think, for instance, Eta Carinae, which is a candidate supernova, it's a very massive star in the southern hemisphere. It's been shrugging off some of its outer atmosphere for thousands of years, which is why there's a large nebula around this star. It's effectively the old atmosphere that's been shrugged off thousands of years ago, and this star is looking very unstable. So we can't tell exactly when it's going to go supernova, but it's predicted to be on this sort of timescale of order. It should have gone off within the next 100,000 years or so. It might be beaten to the punch by Betelgeuse in the northern hemisphere. This is an astrophoto taken by an astrophotographer in which he's artificially brightened Betelgeuse just to show what it might look like when Betelgeuse goes supernova. Betelgeuse is at a distance of about 600 light years, so that's considered to be a safe distance in the sense it's not going to do us any harm, but it should be bright enough to be a spectacular sight at night and probably visible during the day as well. But it's not simply supernova that we have to worry about. When some stars die, like Wolf-Rayet stars, that could be quite serious. Here's an artist's impression of Wolf-Rayet 104. These are very unstable stars that have very high rotations, and it could well be that even though this system is 7,000 light years away, some 10 times further away than Betelgeuse, if this system dies it'll probably produce a jet, a radiation burst in a particular direction dictated by its rotation. And if that jet happens to be pointing towards Earth, well, that could be a problem. Rotational systems like this do produce jets. We think this jet might be pointing in our direction. If it does die and a whole load of gamma rays come through this jet system, it effectively will be a gamma ray burst relatively close to us, and that indeed could be a hazard to the Earth. On a timescale of now jumping ahead 1 square 10 to the 6 years in the future, we're now talking about 1 million years into the future. All of the stars in the Milky Way are orbiting around the center, and Gaia, the spacecraft, has done a wonderful job of mapping out the positions of lots of local stars and making a note of how they're moving relative to us. So we're all going around the center of the Milky Way, but because different stars are going at slightly different speeds, that means some of our neighbors occasionally come close to us and then drift away again. And it's been calculated that one star in particular, Gliese 710, is actually going to come so close, it's actually going to enter within our Oort cloud and then drift away again because of the rotation around the Milky Way center. If it gets that close, because the Oort cloud is gravitationally bound to the sun, this star is going to disrupt the Oort cloud and send a whole load of objects raining down into the inner solar system. So it's been calculated that a close pass by this star is going to result in very bright comets, possibly a bright naked eye comet every month, for perhaps a million years or so, as the star comes into the Oort cloud and then moves away again. But it's interesting to note, not only will that be a hazard to Earth because of the number of comets and asteroids that it effectively throws into the inner solar system, it's nice to think that when that happens, Gliese 710 is going to join the sun, and so we'll actually be in a solar system that contains 2 suns, just like other planets that you all know about. Still on a timescale of 1 million years into the future, why am I showing a picture of meteor crater Arizona? Is that because these things happen once every million years? No. The picture is there so that A, we can remark, what a stroke of luck, it just missed the visitor center. And the other thing we note is that if you do get impacts like this, probably much more often than every million years or so, this one is only a few tens of thousands of years old, weathering on Earth, because of the Earth's atmosphere and because of hot-cold cycles and rain and freezing, etc., the weathering systems of the Earth's atmosphere will get rid of the evidence fairly shortly. In other words, anything older than 1 million years, even though the impact might have happened, we won't see any impact craters, or very few of them, simply because weathering will have reduced them to the point where we can't see the impact craters. So that one we know is recent because it's still fairly obvious. Now that's fair enough on a system like the Earth where we know we've got an atmosphere, but you might say, yeah, but when you make a crater on the moon, it basically lasts forever. Well, no, features on the moon will also erode, not because of weathering in the same sense as the Earth, but because of micrometeorite bombardment. In other words, footprints, like Buzz Aldrin's footprints here, are going to be eradicated by the pulverizing effect of micrometeorites that are continually raining down on the Earth. In fact, it won't be too long before all evidence of the Apollo moon landings will be eradicated by the micrometeorite impact. Okay, it'll take at least 1 million years, but it will happen. So we don't think of it as weathering, but basically things will not last on the moon as long as you might think. Now we're talking 10 to the 7 years into the future, and here we've got Pioneer, one of the Pioneers, Pioneer 10, and they have plaques on them so that anybody picking up the spacecraft knows where they come from. We have the pulsar map giving directions to Earth, and also this little cartoon at the bottom that says this particular spacecraft came from the third rock from the sun. So remember we said that Pioneer and Voyager will be flying through other solar systems every 10 to 100,000 years or so. So what does the 10 to the 7 signify here? That's the length of time it'll take before this plaque cannot be read. In other words, these plaques on the side of spacecraft, even though the spacecraft is traveling through interstellar space, that is not empty. It's full of tiny dust grains. So after millions of years, those dust grains will have impacted the plaque to the point where it'll be so pitted and eroded, it won't be possible to read this anymore. So if Pioneer travels through a solar system and is picked up by a civilization within the first 10 million years or so, then that civilization might be able to read the plaque and figure out where Pioneer 10 or 11 came from. If they wait until something beyond 10 million years, in other words, if it passes through hundreds of solar systems and then 100 million years later gets picked up, then whoever picks it up won't necessarily be able to figure out where it came from because the plaque will be unreadable. 10 to the 8 years into the future, 100 million years into the future, we can ask ourselves what's going to happen to something like, for instance, Saturn's rings. But perhaps before we ask the question what's going to happen to Saturn's rings, perhaps we ought to ask the question, where did they come from in the first place? So we're not sure, but it is thought that a moon, something like a moon the size of Mimas, might have been pulverized to make the rings. You look at a moon like that and you might say to yourself,
that's no moon, it's a space station.
It does indeed bear a canny resemblance to the Death Star, but it is thought that if that's the possibility, it should be possible to do a simulation. If you do a simulation and you take a moon the size of Mimas and pulverize it until it's basically just a cloud of dust, what's going to happen? You might think that cloud of dust just goes round Saturn as the original moon did. But actually, it might be quite surprising to realize that it's not long before that cloud of dust spreads out into a ring system. Look at the time scale. It doesn't take a long time for a ring system to develop. It's only a matter of days or weeks before the dust, because of all the interactions of all the tiny particles, gets spread out into a ring system. And as time goes by, those individual dust particles spiral slowly, slowly, slowly in towards Saturn. So millions of years later, we end up with the ring system that we know and love today. But that process is continuing. All of the particles in the ring system are spiraling inwards and will eventually rain down onto the surface of Saturn. And it's been calculated that on a timescale of approximately 100 million years or so, we can expect all of the particles in the ring system to have rained down onto Saturn, and the ring system will be no more. So for those of you who like to see Saturn through a telescope, get in now, because in another 100 million years, you will not have the opportunity. It's something unique to this particular point in time. And we should remind ourselves about the solar system in generally on timescales of 10 to the 8 years, 100 million years or so. We tend to think of the solar system as clockwork because we all have planetarium software on our phones or iPads, and we can see where the planets are now. We can see where the planets were. For instance, was this the Star of Bethlehem? We can wind the clock back 2,000 years. We can wind the clock forward thousands, hundreds of thousands of years. But we can't wind it forward indefinitely. We have to remind ourselves that even though orreries and tellurians are built basically like clockwork, the solar system isn't. The solar system is in fact chaotic. And so although we can have a pretty good guess of where Jupiter is going to be in 1,000 years' time, we can't tell where it's going to be in 1 billion years' time. It's not simply a question of we don't have the accuracy of our calculations. It is a chaotic system. It's like trying to predict the weather. You cannot tell where it's going to be. Not only that, we don't even know how many planets there will be in the solar system on this timescale. It might be that the big planets have decided to throw some of the smaller planets out. At the moment, things look stable, but that just because it looks stable now does not mean it's stable forever. These, we think, are the timescales on which things will change. The solar system looked very different in the past. We think it could look very different in the future on these sorts of timescales. So we must remember it's chaotic, not clockwork. Still on a timescale of 10 to the 8 years into the future, we know certain things are going to happen. We know that's roughly the length of time it takes the Milky Way to do one circuit. At the distance of the Sun, it takes about 200 million years for the Sun to do one circuit. And what's going to happen with the Sun, that's us there. At the moment, we are sitting in between two spiral arms. The spiral arms are relatively densely populated with stars. We are currently sitting in between two spiral arms in a relatively quiet backwater of the galaxy. But it's been calculated that on this timescale, 100 million years or so, things are going to change. We are going to move from an area in between spiral arms, we are going to move into a spiral arm. In other words, we're going to find ourselves with a lot more stellar neighbours. At the moment, we haven't got that many stellar neighbours within 10 light years of us. But in the future, we could have far, far more. It's difficult to know precisely how many. So what are the consequences of the Sun having a lot of stellar neighbours compared to what we have now? Well, one of the consequences we've already seen. For instance, if Gliese 710 comes close, it disrupts the Oort cloud, it gives us a lot of objects flying into the inner solar system, and some of those will hit the Earth. So that's one consequence of being in a spiral arm, is that's going to happen more often. If we look at the historical record, how often have species been exterminated on Earth? If we look at the extinction rate as a function of time over the last few 100 million years, 500 million years or so, we find that there are spikes where significantly large numbers of species have become extinct. And this tends to happen a few times every billion years, not necessarily once every 100 million, but it's on those sorts of timescales. The last one, the last significant one, the KT, that's the boundary between the Cretaceous and the Tertiary era. That's the impact that killed the dinosaurs and, of course, allowed us to arise. So it's happened before, and it will happen again. This is an artist's impression of one of those rocks coming in from the Oort cloud, heading towards the Earth. If you look at the left-hand side, it looks like that's bad news for Italy. But if the rock is large enough, of course, it's not bad news for one country, it's bad news for the entire planet. So this is going to happen, and it is going to be more likely to happen in 100 million years when we move into a spiral arm of the galaxy. We know that species will be exterminated. The question you could ask is, will we be one of those species? We've got a little bit of time to figure it out. Bruce Willis and everything else, we can perhaps think about diverting some of these incoming comets or asteroids to try and improve our chances. But that's one of the consequences of being in a spiral arm and having lots of stellar neighbours. Another consequence is, if we've got lots of stellar neighbours, maybe one of them could be a supernova candidate. At the moment, we've got relatively few neighbours, well, we've got almost no neighbours that are really massive and are supernova candidates. The nearest supernova candidate is quite some distance away. But if we have a lot more neighbours, maybe that will change. And it has been calculated that a supernova within 100 light years of Earth, well, that could be a danger to us. Remember, Betelgeuse is at 600 light years. That's considered sort of safe. But if it was 100 light years away, 6 times closer, 36 times the amount of radiation, that could be a problem. And indeed, if there's any supernova within 20 light years of Earth, that could be an extinction level event. That could be radiation levels high enough to kill everything on Earth. So it does matter. And if it sounds a little bit alarmist saying we could have a supernova really close, bear in mind it has happened in the past. We have records on Earth of sediments in which we can look for a particular isotope. It's called iron 60. It's a particular isotope which is generated in supernova but doesn't occur naturally on Earth. And it has a half-life of quite a few million years, but it means that because it has a half-life where iron changes into cobalt and then into nickel, if we find any of this particular isotope of iron, iron 60, it cannot have been around since the Earth was born. It cannot have survived 4.5 billion years. Its half-life is simply too short for that. So we do find it in Earth's sediments. And that means that a supernova must have gone off close enough to actually dump this iron into the Earth's atmosphere and ultimately into the Earth's sediments. And it must have happened recently enough that that hasn't yet decayed into cobalt or nickel. So it can't have happened many billions of years ago. So relatively close supernova have occurred in the past and might have been responsible for some extinction level events. If it's happened before, then it is probable that it will happen again. Still on the same time scale as yet of 10 to the 8, 100 million years into the future, this tug of war between the moon and the Earth has been going on for a long time now. The moon raises tides on the Earth, which slows the Earth down, so the Earth loses angular momentum, spin, and the moon gains it and moves further away from the Earth. So that's the consequence of the tides between the two. Earth slows down, moon gets further away. The length of the day at this point would be not 24 hours, not 24 hours and 1 second. The length of the day would now be 25 hours. we'd have to give up the idea completely of adding leap seconds to try and keep the Earth's rotation synchronized with our clocks. We'd basically abandon leap seconds, and maybe this is a good time to decimalize the clock and throw away 24 and start dealing with 25 or 100 lots of a quarter hour or something and start decimalizing things. But then there are consequences to not necessarily the Earth slowing down, but there are consequences to the moon moving away from the Earth. At some point, the moon will be so far away from the Earth, the disk of the moon will no longer be large enough to cover the disk of the sun. So at that point, we will no longer have total eclipses of the sun visible from the surface of the Earth. So again, for those of you eclipse chasers who like this, get in now, because you won't be able to do that from anywhere on the surface of the Earth after the next billion years or so. There will still be partial eclipses, there will still be annular eclipses, where you get a ring of fire around the moon, but the moon simply will not be large enough to cover the disk of the sun. So that's a bit of a shame, but rather more importantly, perhaps, a second consequence of the moon being further away from the Earth is that it will no longer stabilize the tilt of the Earth. Because the angular momentum of the Earth and the angular momentum of the moon are coupled in a physical system, it means that the Earth being relatively close to us keeps the Earth locked at 23 degrees. But it's been calculated that if the moon gets further away by a factor of another 25% or so, then it's no longer going to keep this particular tilt. It's been 23.5 degrees, give or take a degree, for a long, long, long time, according to the fossil records and the sedimentary records. But if the moon gets further away, it's been calculated that that lock will be lost, and then the Earth will be free to change its tilt almost at will. And it could go to 0, it could stay at 23, it could go completely at 90 degrees. The seasons will be utterly erratic at this point once the moon loses its ability to keep the Earth's axis locked in place. So that could be, again, a rather dramatic consequence to the change on the surface of the Earth as a result of how the moon interacts with the Earth. On a timescale of 10 to the 9, 1 billion years into the future, things are going to happen with Voyager. Like Pioneer, which has a plaque on it, which is going to get pitted and corroded on a timescale of 10 to the 7 years, Voyager contains a gold record with greetings from Earth. And it's a phonograph, and that, we think, is going to last for about 1 billion years. Eventually it'll evaporate, but on a scale of 1 billion years, it should survive. And one of the reasons the phonograph will survive is because it's protected by a cover. And so the cover will actually get pitted and eroded, but it will protect the phonograph sitting under that. The catch is that it's the cover that contains the instructions for how to read the phonograph. And also under there's a stylus, because it is like any other LP. So you could say, okay, on a scale of 10 to the 9 years, again, Voyager will have already passed through thousands, if not tens of thousands of solar systems on its journey through the galaxy. If it gets picked up on less than this time scale, any civilization that picks it up will be able to read the instructions and play the phonograph. And again, there's a pulsar map, just like in Pioneer, to tell them where this particular spaceship came from. On a timescale greater than 1 billion years, it might survive, the phonograph might survive, but certainly the cover won't, and we would just have to assume that any intelligence that picks it up is intelligent enough to figure out how to play a phonograph, even though it hasn't got the instructions of how to do so. It's not only instructions on using a stylus, it's also the speed at which you rotate it in order to get the sounds that reproduce the sounds that we want. Still on a timescale of 10 to the 9, 1 billion years into the future, the sun is going to change. It hasn't gone red giant yet, not after 1 billion years, but it is starting to run out of hydrogen and moving towards its red giant phase. When it gets into this sort of region, it is going to be changing its luminosity quite dramatically. Its luminosity will go up by something like 10% every billion years from this point until it actually transforms into a red giant. That means the Earth is going to get very, very warm. It's been calculated that the surface temperature of the Earth would hit something like 80 Celsius. That's a bit uncomfortable. You think it was hot a couple of days ago? No, this is going to get really warm. And I think we can all agree that humanity can't survive living on an Earth at 80 Celsius, so we are going to have to find somewhere else to live and then come back when it's cooled off a little bit. Quite where? Well, who knows? We know the sun is going to expand into a red giant, and we know that the surface of the sun is going to expand until it's something like the orbit of the Earth. So in other words, the surface of the sun is going to come towards us. And the question is, if the surface of the sun gets close to us, is that going to be a problem? Some people say, duh, of course it's going to be a problem. Some people say the Earth is going to get engulfed by the sun, and some people say, no, not necessarily. It's a more complex problem than you first appreciate, perhaps. So we know from understanding the process in other stars, from understanding the evolution of other stars, we know that the sun is going to expand as a red giant, and the red giant diameter ultimately will be about the same as the Earth's orbit. But as it goes through a red giant phase, there's going to be much stronger solar winds, which means the sun will be losing mass. If the sun is losing mass, there's less gravity pulling on the Earth. If there's less gravity pulling on the Earth's orbit is going to expand. So this cartoon on the left-hand side shows that as the sun grows, the Earth is actually going to move away from the sun. So yes, the sun will engulf what we currently think of as the Earth's orbit. But the Earth isn't going to be orbiting at that radius anymore. The Earth will be orbiting further out, perhaps where Mars is or something like that. So the sun will engulf the current position of the Earth, but the new Earth orbit might mean that the Earth survives. The jury is out. Some people believe yes, some people believe no. Let's assume, for the sake of argument, that the Earth survives that particular little episode as the sun goes through a red giant phase. Once it's become a red giant, it will ultimately slough off its outer layers and produce a beautiful planetary nebula, and the core of the sun will be left as a white dwarf. So now we're talking about a timescale of many billions of years, heading towards 10 to the 10 years into the future. The white dwarf will be hot, but relatively small, and the Earth will ultimately cool off. But there's a consequence of not the fact that the Earth is receiving less radiation from the sun, there's a consequence of the Earth simply being very old at this point, and that is the Earth is going to lose its magnetic field at about the same time that the sun goes through a red giant phase. This is nothing to do with the amount of radiation received from the sun. The Earth has a magnetic field because it has a molten metallic core. If you have a molten metallic core that's spinning, it's effectively a big dynamo, it generates a magnetic field. And the Earth's core is being kept molten, not by the sun, but from the heat of radioactive decay of elements that have been sitting in the Earth for the last how many billion years. Ultimately, the radioactive decay will slow to the point where the amount of energy being dumped by the radioactive decay of those elements is no longer enough to keep the core molten. The core will solidify. Once that happens, it no longer is a liquid metal core that's spinning. It's no longer a dynamo. It's no longer generating a magnetic field. So this, we calculate, will happen in about 10 to the 10 years. It might be that this is what happened to Mars. Mars is a smaller planet. It might be that its core solidified a long time ago, which means Mars lost its magnetic field a long time ago, which means Mars's atmosphere was stripped away a long time ago. Because once you lose a magnetic field, you lose the ability to protect yourself from external radiation. In this case, not so much from the sun, but possibly from cosmic rays, which will be beating down onto the surface of the Earth. So they say problems come in threes, that the Earth might suffer because the sun goes through a red giant phase. It will probably suffer because of the loss of a magnetic field. And then what's the third problem that always comes along? Well, in this case, we're going to have a galactic problem. The Andromeda galaxy is going to come crashing into the Milky Way. So at the moment, we have the ability to photograph the Andromeda galaxy with a little star tracker and a telephoto lens on our camera. It won't be long before Andromeda comes so close to us that you won't need a telephoto lens. You'll need a wide-angle lens to get it all in as it comes hurtling into our skies. On a timescale of a few billion years, the galaxies are going to pass through each other. Andromeda will pass through the Milky Way. It's unlikely that the sun will suffer any damage. Remember that galaxy collisions are actually an important part of galaxy evolution. They're not cataclysmic. In many cases, they signal the rebirth of a galaxy, because when one galaxy passes through another, you end up with an enormous amount of new star formation. It's unlikely the sun will be hurt in any way. If the sun gets ripped out of the Milky Way, the planets will simply go with it. So it's not going to be the end of the sun. It's not going to be the end of the Earth. And on a timescale of order 4 to 5 billion years, the galaxies will pass through each other and eventually settle down into one much bigger galaxy. This one indicates that it has two nuclei. The center of the Milky Way and the center of Andromeda both have supermassive black holes. It is probable that they will orbit each other within this new galaxy. What do we call this new galaxy? Milky Way, Andromeda, Milkdromeda, Andrilki. I don't know what we'll call this new galaxy. We've got plenty of time to figure that out, but it will probably have two nuclei, two supermassive black holes that orbit each other until eventually they merge into one as well. So not as cataclysmic as it sounds. It might be a problem, but the galaxy will survive in a new way. The spiral arms will probably be disrupted, possibly stripped away completely. Maybe we'll end up in an elliptical galaxy. This will happen in a few billion years. It won't necessarily be a problem for the Earth. On a timescale of 10 to the 11 years into the future, the slow dance between the Earth and the Moon has finally come to an end, because the Moon has now slowed the Earth down by so much that one day is the same as 1 month. In other words, the length of time it takes the Earth to spin once on its axis is now the same as the length of time it takes the Moon to do one orbit of the Earth. So if you imagine that as two objects always facing each other, just like at the moment when we think of the Moon, we always see the same face of the Moon as seen from Earth. Well, it's going to be the same the other way round. One side of the Earth will now always face the Moon. If you're standing on the Moon, you'll always see the same face of the Earth, just like the other way round has been happening for billions of years. This is also what's happening with Pluto and Charon. They are close enough and tidally locked to each other that the same faces always face each other. It means that from a certain point on the Earth, the Moon will never move in the sky. It'll always be in the same place. And from at least half of the Earth, the Moon will never rise. And so you will only ever see the Moon if you're on one face of the Earth. And if this looks like a Photoshop, this is a genuine photograph of a full Earth and a full Moon. But remember, this is the far side of the Moon, because we're looking at it from outside the Moon's orbit. So this is the far side, not the familiar near side that we normally see of the Moon. It's taken by the Deep Space Climate Observatory some years ago. Finally, we've got to 10 to the 12 years into the future. I've said that the Andromeda Galaxy is going to collide with the Milky Way. Other things will be happening within the local group, the group of gravitationally bound galaxies close to us. The Milky Way is actually surrounded by dozens of smaller satellite galaxies. The Milky Way is going to be hoovering all of those up. So we've already said that M31, the Andromeda Galaxy, and ultimately its partner M33, the Triangulum Galaxy, they are ultimately going to merge with the Milky Way, and everything in the local group will end up in one mega galaxy. It won't actually be a spiral galaxy, it will probably be an elliptical. I just thought that icon looked neater. So we are fairly sure that because all of these are gravitationally bound, they will end up basically cannibalizing each other. So that's on a timescale of 10 to the 12 years. We can ask ourselves on a similar timescale, what's going to happen outside our local group of galaxies? So I've told you before about the idea that you can actually photograph galaxies that are very remote and are receding from us at, in this case, twice the speed of light. As a COVID challenge, I photographed a quasar, the nucleus of a very bright galaxy, that's receding from us at twice the speed of light. As the universe is expanding, and has been expanding for the last 13.8 billion years, we're now talking about so far into the future, all of these galaxies are going to be taken even further apart and be receding from us even faster, to the point where it won't be possible to photograph these very distant galaxies. So on the right-hand side, we've got a Hubble image here where most of the dots you can see are galaxies, and there are just a couple of stars that are inside our own Milky Way. on this timescale of 10 to the 12 years into the future, all of the galaxies, because of the expansion of the universe, are going to be carried so far away from us, it will be impossible for the light to reach us. And so if you think of an advanced civilization at this time looking out into the universe to see, what they will see is nothing other than the stars in their own galaxy. Doesn't matter how good their telescopes are. It doesn't matter if they've got something that's 1,000 times better than the Hubble Space Telescope. If a civilization 10 to the 12 years from now asks themselves, what's out there? Let's have a look at the universe. They will come to the conclusion that the universe is empty other than the stars and nebulae inside their own galaxy. That's a sobering thought, to realize that we can see 1 trillion galaxies, or at least we've got evidence there's 1 trillion galaxies out there, because we live at a particular point in the expansion of the universe. Eventually, the expansion of the universe will take everything so far away from us, it'll be impossible to see. Interesting idea. Now, I said in the previous talk, and at the very beginning of this one, it took 3 minutes to make all of the hydrogen in the universe. 13.8 billion years ago, the Big Bang took about 3 minutes to make all of the hydrogen, and that's what's been fueling the stars ever since. But after a few trillion years, the hydrogen is starting to run out. And so, in principle, there'll be no new star formation. Now, just as an aside, some people disagree with that. Some people say, do you really need hydrogen to make stars? Can't you make stars out of something else? If the hydrogen runs out, couldn't you use helium or any other denser gases, any heavier gases? Some scientists have tried to calculate, is it actually possible to make stars out of gases having much heavier elements rather than gases that are basically just hydrogen with a little bit of helium mixed in? And some scientists have said, yes, I think that's possible. It might be possible to make a star out of heavy elements rather than hydrogen, and have it such that although there are nuclear reactions going on at the core, in other words, nuclear fusion in the way we understand today, it might be possible that the surface temperature is so low, it's even lower than the surface temperature of a red giant, which is a few thousand degrees. Maybe it's possible that the surface temperature could be as low as a few hundred degrees. So in other words, it might be possible to make a star with nuclear fusion occurring at the core, but ice in the atmosphere. Frozen stars. And I'm not talking about Disney's version of Frozen. If that's the picture you've got in your head, then let it go, because that's not what I'm talking about. We're talking about nuclear reactions at the core and cold enough for ice, if hydrogen and oxygen exists, in the atmosphere. Some people think that's a possibility based on their calculations. Other people say, rubbish, you absolutely need hydrogen. If you haven't got hydrogen, you can't make stars. There are reasons that astrophysicists believe that is the case. Hydrogen, in that sense, is special because it is the lightest of elements. So we then have to ask ourselves, what happens next? But before I actually get to that slide, we need to simply say, we need to think about what's happening to the universe in terms of its expansion. And just as a little aside, let's remind ourselves of what we think is going to happen to the universe. This is the size of the universe. Take it as be the distance between any two galaxies you think that are far enough apart as a function of time. So that's where we are now, relative size of 1, and that's us. And the different coloured lines refer to how the universe might behave depending on how much stuff there is in the universe, how much matter, how much energy. So you see the actual age of the universe depends on which model we are using. In other words, depending on how much matter in the universe, that changes our calculation of how old we think the universe is. And it's been calculated that if the universe is full of shed loads of mass, much more matter than we think is actually out there, if it was made of large amounts of matter, gravity will get a hold of it and will pull it back again. We'll be on the orange line, it'll expand for a while, but then it will start contracting, and then we'll end up with a big crunch, a so-called closed universe. But we don't think the universe has got that much matter. We're not on the orange line as far as we know. When I was a nipper, we used to think that we were on the green line. It now looks like, from evidence of the last few decades that we're actually on the red line. That's the amount of matter and energy in the universe according to our best estimates from the latest telescopes and space observatories. That means if you follow the red line, the expansion of the universe will continue indefinitely. Not only that, but notice the gradient is actually increasing. It's not only continuing to expand, it's expanding faster and faster and faster as time goes by. And we don't know that that will ever stop. So we can't be absolutely definitive about this. All we can say is that we've pretty much ruled out the fact that the universe is going to start contracting again. And as far as we can tell, the expansion is going to go on forever and continue accelerating, taking all of the galaxies further and further apart. So in order not to be here all night, I've changed the numbers at the top. Okay? So now instead of each box being 10 times further into the future, each box is now 1,000,000 times further into the future than the previous one. So I'm running out of adjectives to what we call these things. It's not billions and trillions anymore. It's quadrillions, quintillions, septillions, or gazillions. I don't know quite what the correct adjective is there. So remember where we left this thing before we took an aside of what the universe is doing. We said all of the hydrogen in the universe was made in the first 3 minutes, and after many, many trillions of years, it's starting to run out. Now, stars might live a long time. Our sun only lives for 10 billion years or so, and it's about middle-aged. If stars are really heavy, they have shorter lifetimes. Maybe stars that are really lightweight, they could have lifetimes that are trillions, or tens of trillions, or hundreds of trillions of years. But no star lives forever. So if all the hydrogen is run out and you can't make any new stars, what does that mean? There will come a day when there are no more stars shining anywhere in the universe. The age of starlight will come to an end. The stars themselves, when they stop shining, they'll still be orbiting to some extent in their galaxies. There will be these dead husks moving through the galaxy like zombies. There will be white dwarfs, neutron stars, and black holes, basically the dead remnants of stars. You might think it's odd to talk about a white dwarf not shining, but bear in mind there are no nuclear reactions in the core of a white dwarf. It is just the dead core of a star like our sun. It starts off hot just because the core of the sun is hot, but it will cool off. It's just sitting there doing nothing. It will cool off and become a black dwarf. So that's what I mean by no stars shining. Some stars, because of the collisions of galaxies, etc., some stars will be ejected from the galaxy. If the sun is ejected from the galaxy, the planets will simply go with it. Remaining stars will eventually get eaten by the supermassive black hole at the center of the galaxy. So, for instance, we've already mapped out magnetic fields in the centers of other galaxies. This particular galaxy, the magnetic fields have been mapped out by SOFIA, the Stratospheric Observatory for Infrared Astronomy, with an infrared telescope in the back of a 747. Recently decommissioned, by the way, so if anybody wants a 747, watch out on eBay. It should be appearing before too long. So we think that these magnetic fields that are appearing in this galaxy might well be common to all galaxies. It's more difficult to figure that out in the Milky Way because we're inside it. But we think these magnetic fields will effectively funnel matter into the supermassive black holes, which will end up eating all the remaining stars that haven't been ejected from the galaxy. What's going to happen to all of the atoms in the universe? Well, we're not too sure. We know that atoms are made of positively charged particles called protons in the core and in the nucleus, and a whole load of negatively charged electrons buzzing around. And the question is, what happens to protons in the long term? Do protons live forever? Or do they decay? Do they change into something else? If protons do decay, then all atoms in the universe will fall apart. We don't know the timescale on which this is expected to happen. Particle physicists have calculated that it's not likely to happen on timescales less than this, but we don't really know what's going to happen on timescales greater than this. But if they do fall apart, if protons do change, atoms will no longer exist. But it's sort of irrelevant, because even if protons do last forever and atoms exist forever, assuming protons don't decay and atoms survive for a while, there's only atoms in white dwarfs. There were no atoms in neutron stars. There were no atoms in black holes. So the only atoms are in white dwarfs, or now black dwarfs. And even black dwarfs will evaporate eventually. It's an effect I'm not going to talk about in detail, but even dwarfs, black dwarfs, will evaporate into radiation and not leave any matter behind. In other words, there will be no atoms left anywhere in the universe. We know, because of the way black holes behave, for instance, when galaxies merge together, we know that the supermassive black holes will merge together. And so it is expected that supermassive black holes will grow and grow and grow. The one in the center of our galaxy is a few million solar masses. There are some supermassive black holes in other galaxies that are billions of solar masses. It is thought that when galaxies collide and merge with each other, these supermassive black holes could grow to the size of trillions of solar masses. But even black holes are not eternal. Even though you might think that's the ultimate fate of the universe, no, they evaporate. According to our best understanding, it is still technically a conjecture, but to the best of our understanding, we would expect black holes to evaporate. You have to wait for a really long time, which is why the red rectangle is getting really close to the right-hand end of this line here. So why do black holes evaporate? It's an effect that was put together by a number of different individuals, including Stephen Hawking, which is why this effect is now known as Hawking radiation. We know from quantum theory, or quantum mechanics if you prefer, that you can borrow energy from nothing and make particles and antiparticles. You can make matter and antimatter by borrowing energy from the bank of nothing, making the particles, as long as after you've made those particles they annihilate and put the energy back again. As long as that happens quickly enough that no one notices, you're allowed to do that. You're allowed to borrow energy from nothing. How does that relate to the existence of black holes and the evaporation of black holes? Well, Hawking and other people said, well, what happens if that process, which we believe is happening all the time, what if that process happens close to the event horizon of a black hole, here represented by the line? What if you borrow energy and make matter and antimatter, but one of them falls into the black hole and the other doesn't? Now you've got an imbalance. They can't annihilate. So something is different about this situation. It looks like something has been ejected from the black hole. It looks like something is emitted, something is radiating from the black hole. This is what we call Hawking radiation. Here it's in the cartoon a particle of matter or antimatter. Eventually that gets converted into radiation. So we think all black holes ultimately will radiate through this quantum process. And Hawking and others have determined that the radiation increases with decreasing size. In other words, as black holes get smaller and smaller, they radiate faster and faster. So really big black holes are relatively stable and don't radiate much. But as they get smaller and smaller, they radiate more and more. So if you were to watch a black hole, we've never seen this in practice because the process is so slow, but in practice, if we were to wait long enough and watch a black hole, it would radiate more and more and more. The radiation levels would go up and up and up and up until it finally disappeared in a flash of radiation. And even the most supermassive black holes, even the ones that are trillions of solar masses, which will radiate very little, if you wait long enough, red rectangle now at the extreme end of the scale, if you wait long enough, even supermassive black holes will radiate away to nothing and they will disappear. It'll take trillions of times longer than the same process would happen for a solar mass, black hole, but it will eventually happen according to the calculations, according to quantum theory as we currently understand it. So does that mean we've reached the end of time? Well, you could say, let's take a figure of 10 to the power 100, a nice round figure. So 1 Google, not that Google, that is simply a misspelling of the real Google. So the rumor has it that when they set up the company, they intended it to be called that, but somebody got the spelling wrong and they ended up calling it that. So 10 to the power 100 is 1 Google. And it's been calculated that after a Google years, the last black hole that could possibly exist will have evaporated. And so at this particular point in time, there will be no matter left anywhere in the universe. Everything will have been converted into radiation. So radiation will just be floating around the universe, but there will be no stuff in it at all. And after this point, nothing happens other than the universe continues to expand. But there's nothing in the universe other than radiation floating around. And so you could argue time becomes essentially meaningless because there's nothing in the universe to do anything anymore. And I don't normally do this, but just to show you how crazy 10 to the power 100 is, let's actually write it out. So there it is. 10,000 million, you can do it yourself. It's a very long time into the future. Just because we can't imagine how ridiculously long that particular time period is, does not mean we can't do the calculations and say, if this bit of physics is right, if this is the mass we start with, if this is how Hawking radiation works, we can calculate that it takes this many years for the largest black hole to evaporate. Just because our imagination is limited doesn't mean the maths doesn't work with us to tell us these are the timescales on which the universe will effectively come to an end. Again, we can ask the question, what's it like at the end of time? Well, some people have said what it's like at the end of time. Eternity is a very long time, especially towards the end, says Woody Allen. I prefer the cartoon XKCD, which has an interesting insight into humanity as related to the rest of the universe. They say a human is simply a system for converting dust billions of years ago into dust billions of years from now via a rather roundabout process, which involves checking email quite a lot. So, as not to leave you too depressed, let me finish with a little bit of an epilogue. You could say that we live in a golden age. The sun is middle-aged. It's about halfway through its 10 billion year life. It's middle-aged and stable and well-behaved. We have a moon that's at just the right distance to stabilize the Earth's axis and stabilize the Earth's seasons, which makes life nice for us. And as a little aside, it also gives us the spectacle of a total eclipse of the sun, as seen from the Earth's surface every now and again. And thanks to evolution, we are able to explore and discover and understand the universe in which we live. And we can do that by building spacecraft, which we send out into the solar system to explore our immediate neighbours. And we can build telescopes that allow us to look out into the universe and see billions of galaxies at distances of billions of light years. And we could not have done this in the far distant past because we needed generations of stars to go through the nucleosynthesis of making elements. We needed generations of stars to convert hydrogen into helium and convert helium into carbon and nitrogen and oxygen and calcium and phosphorus and iron and all the elements that we need to make us us. And as we've just seen, in the far distant future, the universe will be dark and the universe will be boring. So the best time to exist is quite definitely now. Thank you all for listening.